Yeah, I'm going to show you the sheet. I'll share it on this page. I'm going to go through it. It's the one that's typed out. This one, magnetism direction practice. This was the one I had asked you to do for homework a couple days ago. We didn't get a chance to go over it yesterday. Okay, so when you're getting, this was a hand-in assignment at one point. I'm going to try to like go through some of this with you so you can see how I'm solving it. Now, first of all, whenever we see that it's an electron written here, okay, that means that it's an electron flow. So I'm automatically saying to myself, use your left hand. And I'm writing that down just to make sure. Okay, so use my left hand, put my thumb in the direction of the flow of the electrons. Okay, so my thumb is going in that direction, curl my fingers around. So it's like I'm holding on to that wire and my thumb is pointing in the direction of the flow, but it's my left hand because of the electrons. And then I draw my magnetic field and I label it as the magnetic field. Now, I'm only drawing one. There are multiple field lines that would be surrounding us, that they would be expanding outwards in the wider direction, so there would be lots of magnetic field lines. I'm just drawing one. For letter B, the magnetic field is provided, and it's going clockwise, so my fingers should be going around clockwise. I'm using my right hand, so I should indicate that the conventional current is going into the page. Now it says provide the magnetic field, current, electron flow, force, or type of charge. You don't have to do both of these, right? Just choose one of them, but make sure you label which one you've used. Okay, and obviously I'm not doing a force because there's no force going on and there's no type of charge to do. That's for talking about later. I was trying to make one instruction that fit all of them. Sometimes that's not really the best way to do it. Okay, my fingers curl up and over for my magnetic field here. Again, I'm still using my right hand and the current is coming along the wire, making sure I label that that's conventional current. Down here we have an electron, so that tells me use my left hand. My thumb is going into the page. I need to go up a little higher so you can see my whole hand. Sorry about that, people. Okay, so my thumb is going in the direction of the flow. Curl my fingers around. Didn't realize I had so many freckles until I started to do this. So then my fingers are coming around this way to indicate the magnetic field. Again, I'm just drawing one to represent many. I don't need my page to look too messy or too like crazy right now. But on a test, yeah, you might want to draw more, right? I might show you will have more space. That's provided we're doing any of it in person. If this is, oh yeah, this is another thing, right? The hand rules are so nice to do if you have the paper right in front of you. Hate this part. Okay, so this was all hand rule number 1. Here we have hand rule number 2. So when I see the battery, the first thing I think of is this is the positive, this is the negative. So this is actually just a single cell, so I really should not technically call it a battery. The magnetic field lines leave from the north and enter at the south, yes. So here my fingers come around, up and over. So now my positive, even though we know it's wrong, the conventional current leaves from the positive, curls around, and yes, it's coming in around behind, even though we can't see it, and down in through here. So there's my conventional current. So that was the first step. I needed to find the direction of the current. Then I'm going to use the hand rule. So then my fingers, so this is opposite to hand rule number 1. My fingers are going to go up and over and curl around, and my thumb is going to indicate the north. So that puts the north right here and the south over here. The magnetic field lines leave from a north, so the flux lines, which are called the magnetic field lines, leave from the north and enter at the south. So I would put arrowheads on that. Leave from the north and enter at the south. Notice I'm not drawing any magnetic field around this section of the wire, because that's very, very small magnetic field. The concentrated magnetic field is occurring due to the solenoid, due to the coils of wire. These are leaving from the north, entering at the south. But I was a little bit hesitant because Joyce's question says, is magnetic field always from north to south? Well, we leave from a north and we enter at the south. If I were to put a compass in the center of this solenoid, it would actually complete the circle, kind of like the domains of a bar magnet would. Okay, so that means it's like there's a pretend bar magnet here. So these, if a compass was sitting in here, it would actually line up in this direction, completing that circle of the magnetic field. Okay, when we have a bar magnet, we draw the magnetic field lines leaving from a north and entering at a south. It's only in the interior that we show the domains acting in this direction, or that we would show that a compass inside a solenoid would look like that. Okay, again, I could draw more lines, whatever we need to. So here we have a positive, we leave from the positive, go up and over, fingers curl up and over, so then I have a north here and a south here. I should indicate that that's conventional current as well. Now, I'm not going to draw the magnetic field every single time, but on the test, I would like you to draw the magnetic field. Okay, here my thumb is going to go in the direction of the north, curl my fingers over. So my fingers in the front of the solenoid are going in this direction. So then I extend them outwards here, which meant it left from this side. So that's my conventional current. So this is the long side of the cell. And I'm just going to put a few until I fit it in there. It doesn't matter how many you draw. I'm not going to like say, oh, there has to be 2, or there has to be 3, whatever. As long as I see a long and a short in the correct orientation.
Miss Pi?
Yep.
For this one, could we do electron flow?
Yep, absolutely. As long as you label it, yeah, as long as you label it as electron flow. So then the electron flow would be going in the opposite direction, okay, because I'd be using my left hand. My thumb would go up and over, but we would get exactly the same answer, right? Because I would see my electrons going this way, which would mean the electrons would leave from here and come in here. And so there's no requirement, because some people just, maybe because they're right-handed, they just want to use their left hand. Yes, that's totally okay with me. Okay, for letter H, the electrons, this one, oops, electron flow, so make sure you use your left hand. So my electrons are flowing up and over, coming down this way, so then I have a north here and a south here. If I continue with these electrons, they come into here and they left from this side. So that means this is a short side and then a long, and then as many as you want to put in there to fit. Okay. Again, I didn't draw the magnetic field line just because they end up all like kind of blending together if I draw too many of them there. You don't have to draw in the conventional current there. It has not been requested. It's either or. Now for I and J, sometimes people aren't sure what to do. This is just a bar magnet. So that means we should just see the magnetic field lines leaving from the north, entering at the south. You could draw multiple of them. That would be fine. Actually, I'll go here. There's not a formula for exactly how many you need to draw, as long as you're showing me that you know the direction that they are leaving. I should be able to see they're leaving from the north and they're entering at the south. And it should be fairly symmetric, right? Where the above the bar magnet should look something similar, although, you know, my drawings are not the greatest, so I'm okay with that. Now here, when we have two north, so these could be the north ends of horseshoe magnets and we don't see the other side because there's no such thing as a monopole. Or this could be the situation where there's a north standing on end, and we're looking at the north beside another north. So what's that going to look like? It's going to leave from the north, but then it's going to veer away. So we're going to see that repulsion pattern. Right, so as long as you're showing that there's some kind of a zero area in between, and then the fields are going away from each other.
Would it be okay?
Yep.
If we just drew the lines on the outside edges of the north ones and then just kind of drew the arrows going away? Like nothing in between the two norths, just on the outside. You should show that there are some, like the main repulsion is going to happen right here, but so you should show something around in this area. A little bit of repulsion, because there should be kind of like a line through here that would be like the zero line, like the zero magnetic field location kind of idea. So ideally there would be something here. These were a little close together. If they were further apart, then for sure you would need to show something. Okay, does that answer your question? Yep.
Okay, so then for K, this is hand rule number 3. Again, it says electron flow, so I'm going to use my left hand. I'm going to put my thumb in the direction of the electron flow. My fingers are going to point in the direction of the magnetic field, and my palm is facing upwards. Or I said, like, you could use your fingers to say, oh, look, that's pointing upwards. So then the force is going to be out of the page. Okay, and then for letter L, tell me if I'm going too fast or you need me to go back through something. Right, now here the magnetic field is indicated that it's going into the page. Here's a proton, so I'm going to use my right hand. This is an electron, so I'm going to use my left hand. This is my velocity, so read really carefully which thing has been provided. Okay, now this one is a little bit uncomfortable, so I might rotate this paper. This is the advantage of having the paper in front of us. Put my thumb in the direction of the velocity, and my fingers are going into the page because the magnetic field is going into the page. So these fingers are the magnetic field lines, so they should be going in. My thumb should be pointing that way, and my palm is facing in this direction, so that's the direction of the force. I tend to draw it somewhere near this edge, like not at the end of here, but it's not going to be wrong if you drew it there. Okay, I just kind of considering this as the proton. Yes, question? Yeah.
For this one, wouldn't the force be like in the opposite direction?
Okay, so you're using your right hand, correct?
Yeah.
Okay, so your fingers are going into the page. And your thumb is pointing in the direction of the velocity. So the tip of my thumb is like this arrowhead. And so my palm is facing this way.
Yep, I was using the wrong hand, sorry.
Oh, yes, yeah. See, that's a huge deal, right? Like that's what I want to make sure that everybody's like super careful about. Like, yeah, that's why it's nicer if you do have a piece of paper, because you can kind of highlight it and say, wait a second, this is a little weird. So now here, I'm going to rotate it around the other way. Now, electron, use my left hand. Okay, so fingers are still going into the page because the magnetic field is still going into the page. This is my left hand. My force is acting towards the top of the paper, so my palm should be facing that way. So then which way is my extended thumb pointing? I should have a velocity going that way. Okay, so be really careful. What have they provided? They provided the force and the magnetic field. Find the velocity. Someone is making coffee. It smells really good. I don't like coffee. I don't drink it, but I like the smell of it. Isn't that weird? So someone somewhere is making coffee and it smells nice. Okay, now I'm going to rotate around. Sorry if you're like trying to do this and I keep spinning things. But for letter M, what I might suggest first is draw in the magnetic field lines, because we need to have our two things that we're using in order to find the third. Okay, ooh, that kind of hurts my hand. This is going to be right hand, so I'm going to rotate it again. the current, oh no, that's, current is going into the page. I'm going to totally spin this around. Okay, current is going into the page. You guys are like, stop moving the paper, Miss Pye. Thumb goes into the page because of that X. Fingers are going in the direction of the magnetic field. Okay, so these fingers are going from the north to the south. Then which way is my palm facing? It's facing this way, so there's my force. That was my right hand because of conventional current. I drew in the magnetic field lines. Okay, looking at letter N, we leave from the north and enter at the south, so there's the magnetic field lines. I am using my left hand because it's the electron flow. Okay, so my thumb comes in the direction of the flow. I have to, flip my hand over. I'm going to move over so I can kind of do this. It's like, hurts my hand. Okay, my palm is facing upwards. Boy, the veins in my hand really show up when I do that. Okay, so that means the force is going to be out of the page. Okay, so again, being really careful that we're using our left hand there. Some people actually prefer to switch everything to the conventional current and then draw in the conventional current because it would be in the opposite direction. Thumb goes in the direction of the conventional current, fingers go from north to south. Oh, same direction, force out of the page. Okay, it should agree no matter which way you do it. Okay, I'm going to flip over to the other side. Okay, hopefully everybody has that one. I am recording, so then you can go back if you need to. Okay, now this page sometimes causes some stress because it says indicate with a positive, a P plus, an E minus, or an imp, which first of all, people are like, what is imp? Whether the following situations represent the force felt by a proton, electron, or an impossible situation, right? So this is just, you know, it doesn't work with the hand rules, does not follow hand rules. Okay, so now the entire magnetic field is into the page. So all of these things, so we're basically just taking our two hands to see which things work and which things don't. I can automatically see that there are two things that are impossible, and I'm going to deal with those right away. If I have a velocity that's coming this way, there is no possible way that the force is actually acting in the same direction. They are always at some angle to each other. So this is an impossible situation. And also here, if the velocity is in this direction, this is also impossible. Okay, we can't have a velocity in one direction and then the force, because your thumb and your palm cannot be parallel to each other. How that would, like, if you had to bend your thumb back to point that way, no, it doesn't happen. You also can't bend your thumb back to go this way. Maybe some people can because they're double jointed, but that's not what you're supposed to be able to do. So you can't move your thumb to point that way, and you can't move it to point this way. So those are some situations that wouldn't work. Now, some people want to say these are impossible, but these are not. And we already covered mass spectrometers. So we do know that they do start to circle. So if we start with these and say, well, if this is the direction of the velocity, okay, now they should be labeled. That's one of the problems. Like if I think about if the velocity was going this way, so let's start with this one. My fingers would go into the page, my thumb would be in the direction of velocity, and my palm would be facing this way. So that would mean that there would be a force exerted in this direction, which would cause it to circle. So this would work for a proton because the force would continuously be acting towards the center. So it would work to circle in that direction. What about this other circle? If the thumb was going this way and fingers are going into the page, oh, now the force would be acting out of the circle. That's not possible. So that means, losing my hair, thumb going in the direction of velocity, fingers into the page, palm is facing left. Oh, that works for my left hand. So that tells me that this is an electron that could feel a force in this direction. Well, what if I use the other side? Velocity coming down, fingers go into the page. Oh, my palm is facing this way. Yes, then it is going to circle because it has a centripetal force due to the magnetic field. Okay.
Why wouldn't that one for your right? Why wouldn't that one work for your right hand?
Because if we were here, thumb going this way, fingers going into the page, the force would have been out of the page, which would cause this to circle in the opposite direction, not a clockwise circle, but a counterclockwise circle for that direction of motion. Right? It has to work that the force, which would cause that circular motion, would follow the hand rule. So let's try a few more, see if that kind of makes more sense. So like, let's take, we're looking for velocities, right? So our thumb has to be the velocity. So let's take the top one up here. Thumb would be velocity. Oh, that one hurts again. So I'm going to rotate the paper. Thumb would be velocity. Fingers are going into the page. So that means my force is going that way. Oh, but my palm's facing the other way if I use my right hand. Okay, so this doesn't work for the right hand. Does it work for the left? Thumb is going in the direction of velocity. Oh, yes, it does. So that tells me this is an electron because it worked for my left hand. Okay, how about over here? Thumb go in the direction of velocity, fingers are into the page. Every single time my fingers are into the page because the magnetic field's the same everywhere. So then if my palm is facing in this direction, oh, that's a proton. Kind of annoying probably that I'm writing it sideways. Sorry, people. Then velocity here, fingers going into the page, palm is facing that way. So this would also be a proton. Here we have a velocity into the page. Oh, wait a minute, palm's facing the wrong way. So then thumb goes in the direction of velocity, fingers are facing in this direction. So that's an electron. Did I really even have to use my left hand? As soon as I see that it's opposite, then I could even automatically just write the electron. But sometimes people like to confer. For this one here, thumb goes in the direction of the velocity, palm is facing over to the right, so this is working for my left hand, so that's an electron. And here, velocity is upwards, palm is facing to the right, so that's also an electron. Okay, so that was a lot to practice all at once. How do you feel about those? So these are all using our, this is really technically hand rule number 4. Okay, and then the part that is usually people's least favorite, this is our reading comprehension, right? So for each of the following, draw the diagram for the situation and find the missing information. Okay, now that we don't need to be as far away. So a wire lies in the east-west direction with current flowing east. So it mentions current, so then that's going to be conventional current. A compass is placed above the wire. So I have a compass above. What is the deflection of the compass needle? So you want to imagine that this is the wire. Here's the compass. It's sitting on top of it. So that means that the current that's in the wire, so my thumb is going to the east, my fingers are curling around. The compass is placed above, so I want the tangent to that part of the curving magnetic field, right? It's taking a direction at that one location. So that means we would see our fingertips were pointing downwards, so that means the magnetic field would be acting south for our direction. Okay, now this one, I did not leave very much room, so it's kind of annoying, but a solenoid sits vertically along the plane of the paper. So here's the solenoid. It's sitting along the plane of the paper. So in other words, it's like part of the paper. So if I'm sketching that solenoid, it would look like this. Okay, it's not sitting vertically this way because that's perpendicular to the plane of the paper. So you wouldn't draw it as a circle. So if I said, you know, the solenoid is sitting vertically so that it's coming towards you, then that's what we would draw there. We would just draw the circles. Okay, so it's sitting this way with the north of the magnetic field located in the true north. Now, why do I have that, and why does it have brackets around it? True north. Okay, so when true north, yes, that's a good Jets thing too, right? True north, yes, okay, good. Jets got to win. Oh yes, anyway. So even though we have our geographic north, right, we know that that is technically a south pole. So if you took that to mean that this was going to be a north, then if the thumb was pointing in the north, our fingers would curl around. It says show the current, so I want to use my right hand. Right hand. Curl my fingers around. My fingers are going to be coming from the left up and over. Now, if you were like, oh, wait a minute, by true north, she means it would be going the other way and it would actually be a south, then you would draw a south there. So here the current is kind of flowing. Sketch the current and the magnetic field. So we would have a north, we would have a south, leave from the north, enter the south, etc., etc. Should do more than one. Okay, so then if you flipped it the other way, I would still accept that because you could technically say, well, is the true north really actually a south? So if you put a south there, then we would see the opposite thing and the north down here leaving from the north. So again, it's all that interpretation. I will make sure it's obvious. This is just an old quiz that I used. So leave from the north, enter the south, going back down through here. So I'm showing the direction of the current on the inside as well. Or not the current, the magnetic field, sorry. A current conductor lies so that the current is coming out of the page. It sits in a magnetic field directed to the west. What is the force acting on the wire? So my thumb is going to point in the direction of that current. My fingers are going to the west. My palm is facing south. So you can't just write south. You're going to need to draw the picture because it said draw the diagram. Okay, so you may have to do this on the test. That would be the hard part. Okay, so a proton is shot south through a magnetic field directed out of the page. They should be relatively the same distance apart. That's kind of my bad there. I'll just make that the B. So the magnetic field is coming out of the page and the proton is shot south. What is the force acting on the proton? Make sure you're using your right hand. My thumb is going in the direction of the velocity. Oh, again, we're kind of close to my hand. And fingers are coming out of the page. So my force should be acting west. An electron enters a magnetic field directed to the east. The force felt by the electron is to the north. What is the direction of the electron's velocity? This is our left hand because it is an electron. So I have the force, so my palm has to be going that way. So it's easier with my hand. Okay, so my fingers have to, these fingers are going in the direction of the magnetic field, but my palm has to face towards the north. So I had to rotate my hand. So yes, there's my magnetic field. Oh, but the force needs to be that way. So I rotate my hand. My thumb is therefore, when it's extended, pointing into the page. So the force would be into the page. Okay, I would prefer you wrote the words out because the dot or the X is a little bit more inaccurate. Okay, so I'm going to put that one away. You have another one that I will go through on Monday. I'll just post the answers then. You have this one as well, which is the right-hand rules quiz number 1. No, it's not a quiz. You do not have to hand it in, even though it says quiz on it. It was an old quiz. So was this one. So that's why sometimes it has marks on it. On the back side is another quiz. So you got lots of practice. Here there's a compass below. So you want to imagine that the compass was here and then the wire was sitting on top. Okay, so you're just trying to visualize those things. So for Monday I will post the answers for that one, or I'll show them. I'm not going to go through them the same way we did with this one because that just takes a lot of time. I'm hoping that after today you're feeling a little bit more comfortable with that. You will notice on the hand-in assignment, okay, so that's for Monday. On the hand-in assignment, there is a little section, which is due on Monday. There is a little section of the missing information, magnetic field, current, or force, right? So I need to know where things are for those things. Can you tell that this is conventional current and those arrows are kind of hard to read, but they're pointing downwards, right? What particle is this one, right? If something is given, here's the current, here's the magnetic field. Okay, what's the direction of the force? What's the thing that's missing is what I'm looking for there. Okay, so this is the hand-in one. I'm going to put a spot on Edsby for you to upload this. If you could please upload it as one document, that would be super helpful to me. Okay, because then if you like take your 4 pictures and then create one document and then upload that all at once, that would be super awesome. If you can't do it, I will get by, I will be fine. But if you can put it as one, that would be great. Okay, so that hand-in assignment due on Monday. Okay, then you also have, okay, one last thing we need to do for our notes. So let's go through that. Yes. Okay. Let's turn to our notes now because I'd like to just finish up the last topic so that we're ready. Hello.
Can you help me water something?
Okay.
Okay.
So we're going to stop presenting this one. I'm going to switch to the whiteboard.
Do you need extra storage system? Do you need a system?
I just moved the nervous system.
Okay. Okay.
Okay, so our last topic.
Yeah, the extra storage.
Maybe just shut this off so it don't have to look at me. Okay, so the last thing that we need to look at is the force, and I had kind of, oh, actually, I could even go to that. Where is it from yesterday? It's opening, but I don't know where it is. Oh, there it is. I don't know why it's way off to the side. Okay, so this is what we did yesterday. Sorry, just you're having to like watch me scroll slash not really working very well. Okay, so what? Okay, I don't know how. Oh, maybe because I put 2 fingers on there. Okay, so this is what I sent you home to do. We're looking at the force acting on parallel current carrying conductors, the direction and the magnitude. So I gave you those 2 equations and I wanted you to try those out. maybe it's easier if it is on a separate page. Okay, so we're going to go back to that new whiteboard. So we have the force on long parallel wires separated by a distance. Okay, so we started with the wires with current in the same direction. And we had them a distance r apart. And we have a certain length of those wires. So L stands for length. R stands for the distance between. Or the separation. Now, I had given you the hint about the magnetic field strength around a current carrying conductor. So if I look at I1 and I think about that one first, if current number 1 has current flowing towards the top of the page, then if I put my thumb in the direction of the current, I should be able to get the magnetic field curling around so that B1 is going around and inwards, right? So I could draw many, many of those if I wanted to. I could draw them over and over again, but then it just gets kind of confusing if there's too many. So our magnetic field strength from wire 1. So wire 1 creates, so wire 1, which is a current carrying conductor, generates a magnetic field B1 using the equation. B1 is K I1 over R. Wire 2, also a current carrying conductor, is now in a magnetic field. So the current carrying conductor in a magnetic field will experience a force.
Is it just in a field because of wire 1?
Yep, exactly. It's only there, like there wasn't a field anywhere. Yes, there might have been the Earth's magnetic field, but it's so small we usually can ignore it. It's now in a magnetic field, and you could call that the magnetic field B1. Okay, so then the force that it experiences, the ILB sine theta, so this is the force that wire 2 feels as a result of 1. So we'll go here. Force on 2 due to 1. So that means the current that I2 is feeling is a result of the magnetic field from 1. The angle between them will be 90 degrees. right? Because if we consider that, if we were to look from above, we would see that this is coming directly in and would be perpendicular to the wire. The wire would be sitting vertically and the magnetic field would be sitting horizontally if we were to consider that. Okay, so if this is V1 right here, that means this value can come in here. So our force of 1 acting on 2 will be I2, L, just the length of the wire, that's L, and then I'll have K, I1 over R, the distance between them. And I'm not going to include the sine theta anymore because we've already eliminated it. Now, a little bit nicer way to write that, because it's looking all a little bit messy, is we usually would put the K first, and then we would have them in decreasing order, I1, I2, L over R. So this is the force of 1, oh, where did we go? Mine disappeared off my screen, sorry. That's the force of 1 acting on 2. But what about the force of 2 acting on 1? Let's go back. Looking at the same, yeah, it should be the same, right? If I now consider, let's draw this again. Here's I1 and I2. I'm going to make it a little bit bigger because that looks really small. Some of you are on your phones, I know. Okay, so we have I2 coming up here. If we consider I2 and we draw its magnetic field, so our thumb goes in the direction of I2, our fingers curl around, and we have here B2's magnetic field. So yes, there would be lots of them. I could draw lots of them. They could be smaller, expanding outwards, yada, yada, yada. It's all there. We know that these are R apart still. And we have a current of I1 going through here. So in the same substitution, I could say F was going to be I1 LB2 sine theta. So I would have F, this is the force of 2 acting on 1 becomes I1 L KI2 over R, and then the sine theta, this becomes 1. If it was 0, that would be bad. Everything would become 0. So notice this becomes exactly the same. K, I1, I2, L over R. So our equation for both of them can be written in general this way. This is the force between current carrying conductors usually they are long parallel wires. Now there's something interesting. We did not look at the direction. Okay, I did mention in your homework that you should also look for the direction there. So if I go back to just right here, if I say, okay, we need hand rule number 3, sorry, I'm just trying to pick a color. If it will let me pick a color, change color, come on. Right, no, not gonna let me right, okay. Change the size, move it around. I don't know why it doesn't respond sometimes. Sometimes I need to tighten the cap, but no, that's okay. Okay, now it's letting me switch. So if I go now to look here, so my thumb is pointing, I'm gonna follow the current, So my thumb is going to point in the direction of the current. My fingers are going to be coming out of the page. Okay, so here the B is out of the page at this location, right? The current is going north. So my thumb is that way. My fingers are coming out of the page. So then I should have a force that's acting in this direction. I'm going to sneeze. Excuse me. I don't know what about that made me sneeze, but. Okay, then let's go back and look at the other one. Here, I have the orange part, which is going into the page. Here, the B is into the page. Okay, I'm switching colors all of a sudden. Into the page at this location, right? So now my thumb is going up in the direction of I2. My fingers are going into the page because of the magnetic field from wire 1. And my palm is facing, let's say here, my palm should be facing this way. Okay, so in general, if the wires have current in the same direction, there is a force of attraction. Between the wires. If the parallel wires have current in the opposite direction, then the force will be repulsion. Okay, so that means that, like, if I had current going down and in the other one, current going up. So if I1 was going up and I2 was going down, you can see that that's going to change the direction of the magnetic field. So I2 pointing down means that the magnetic field is now coming into the page here. So my thumb is indicating the direction of the current. My fingers are going into the page. So then there is a force acting outwards here. If I do the same thing for here, show the magnetic field 1, it's going into the page. Thumb goes in the direction of the current, magnetic field goes into the page, then it feels a force outward. So there's repulsion away from each other. Now this is important because we do have wires that are strung up along towers. So when we have wires that are hung near each other, they may push away if the current is flowing in opposite directions, or they may move towards. Now that's only if there's DC current, right? So this is a phenomenon for DC current. If we have AC, they're switching directions so often that we don't see this as much of a problem, but we do ship or transport some current through wires in DC. It now is a possibility. They used to always just ship it in, shipping it sounds like a weird thing to say because it's traveling through a wire. It's not going on a truck or anything like that. But when they're traveling it through a wire, they have found that for some instances, using high voltage DC can be a possibility. We will talk about that when we get into the AC current discussion next week. So we will talk about kind of the choices that are there. Now, this equation or this application is also used to define current. The definition of current. Well, really, the definition of the ampere. 1 ampere is the force. Oh, no, sorry, never mind. The current, I gotta say it in a different way. The current, oh no, don't do that. It like, if I write too fast, then it corrects it later. Current through each of 2 long parallel wires separated by 1 meter experiencing a force of 2.0 times 10 to the -7, sorry, newtons per meter. Okay, so what this means is kind of like a standard. It's a standard way to say 1 amp of current. Okay, so if these wires have a force moving towards each other of 2.0 times 10 to the -7 newtons for every meter of length, then we know there for sure there is 1 amp of current flowing through that. Now you'll have to notice this is like a newtons per meter, so it's a force per unit length. And you may see that occasionally where we take our equation, F is equal to K I1 I2 L over R, and we divide both sides by the L. So if I divide this by L and I divide this by L, then we get a force per length. Okay, so this is sometimes more common as the force per unit length. Force per, I don't want to say that. Force per length. Force per meter is quite often what they'll say. Because they don't necessarily want to, like, say, I've got 1,500 kilometers of wire. No, they'll say this is the force that I feel per 1 meter of wire. So quite often it'll be written that way. Okay, for homework, I'd like you to do the mass spectrometer page. Number 7 to 10, these relate to these. You have your magnetism hand-in assignment. If you are finished all of that, then you could get started on your magnetism review. Okay, so there's a bunch of stuff to get started working on now. Are there any questions? The bell just went. Some of you may have some stuff that you have to do for classes, but any issues or problems? Oops.
The magnetism and in assignment is to and in.
Sorry?
Do we have
Yes.
to?
The magnetism hand-in assignment, you're going to hand that in, and you're going to put that in EDSB. So you're going to take pictures of your answers and put that on Monday. Oh, sorry, I was not checking this. Is this just carrying on? Yes, it is carrying on from yesterday. Where did the formula B equals KI over R come from? That's the magnetic field strength around a current carrying conductor. That was Ampere's rule. Yes, oh yeah. And then K is equal to 2 times 10 to the -7. That's why that is the force per unit length, because that's our constant. DC is, yes, direct current. Oh yeah, we don't need to say direct current to direct. No, that's fine. Yes, it is redundant to say the current again, yes. But if we say it's DC, then sometimes people don't realize. Okay, any other questions? So yes, I will put that up on Edsby today, the hand-in section, like where you'll have your online submission for Monday, and that's about it. So the rest of the stuff will not be for hand-in, so the review, there is unfortunately not an answer on the review. I do have answers for it, so I will post the answers there as well. Okay, any other questions?